Hello and welcome everybody. My name is Schrondinger'S Chakraborty. Today I thought that I must say something about the so-called Schrondinger'S equation about the quantum space and time. That relevantly gives us about the brief idea about energy and the displacement quantity and momentum factors about the quantum and time space realm. So when it comes in terms of quantum and time space, so we all are quite enthusiastic and eager to know about, as humans have a very tendency to know something that are not known to them. So that's a wide eagerness. From that the learning eagerness comes. So today I thought I must describe one of the very interesting and fun facts about the equation, the quantum equation, Schrödinger's equation. So the equation starting quite look like this. The psi, the wave function is this. This. This one is the preliminary equation actually, and then we need to do some even more calculations in this. So that will eventually look like showing. So the energy equation, as we know, the quanta of energy, the slightest energy, that the minimum has to be from the old quantum theory. We know, say E equal to h equal to h. That can be even depicted as the h cut format and omega format. That is from linear frequency to angular frequency, and h to reduced h or h cut. And then again, as we know, this very equation, h equal to lambda by p, the de Broglie's equation of duality of wave and matter. And on further some calculations, we will see how it turns out to be an h cut equation of momentum itself. So the equation turns out to be like this. The duality equation, lambda equal to h by p, turns out to be p equal to h by lambda. And on further calculation, we can see the h by 2 pi and here multiplied by 2 pi by lambda, that is the wave vector that represents the directional unit vector of the wave that's traveling, and this is h cut, the reduced h. So it turns out to be p equal to h cut. So far we have discussed about the wave function itself, the preliminary one, the one that is with the momentum and that's with the angular frequency and the wave vector format. So we tend it to be in the form of energy and momentum. So how to do? So the reduced h formats of momentum and energy that we got, so we would further implement it in the wave functions equation. So let's see how it turns out. So on further calculations, we can see the omega turns out to be e by h cut and the k turns out to be p by h cut. So on putting those values in the equation of psi, we get the relevant equation that will help us on further knowing the equation. So here we can see the relevant wave function equation, and here we can see an equation from the classical mechanics that states the total energy is the equivalent summation of the kinetic energy and the potential. energy. So here you can see the p square by 2m format. We are very used to the half mv square format, that is p equal to mv, that's p square gets mv square, right? So and by 2m, that turns out to be the m gets cancelled out and the m square becomes m and v square remains v square and half is in down. So you can see the new format is p square by 2m. That will be relevant from now. And the v ends here the potential energy that a particle has. In further discussions we will see in box potentials and square wells and finite wells, this is come in handy. On the next step we can see we merge the classical equation with the wave function that satisfies and describes the quantum realm. So we get a semi quantum equation that represents the energy, that is E psi equal to p square by 2m psi plus v psi. And now our work will be to find what is E psi is and p square by 2m psi is, because v psi is quite well defined for this very case, as it is the potential energy. So to find the E psi, we would be doing the time derivative of wave function. To do that, we would differentiate we would differentiate the wave function with respect to time to get the first derivative of wave function with respect to time. Let's see what we get. So as we can see, the first derivative of wave function gives us the minus of I by h cut E psi. And on further calculation, we can see E psi equal to I h cut d psi dt. How this comes? I square turns out to be minus 1. If we multiply up down with I, up becomes I square and down becomes I, and I square and minus I becomes plus. So if we just interchange the sides, we'll get this. And now the p square by 2m psi, for doing that or getting that value, we need to doubly differentiate the wave function with respect to the position of the particle. So we can see we just differentiated the wave function with respect to position of the particle, and we got I by h cut p psi, and then again we differentiated the same again with the position with respect to position, and we get I square by h cut square p square psi, and we divided by 2m on both sides to get the p square by 2m. So we can see a quite relevance here, p square by 2m psi. So on further calculations, here we can see p square by 2m psi equal to minus h cut square by 2m d2 psi dx2. So our first equation was E psi equal to p square by 2m psi plus v psi. So how it turns out to be? So the final equation turns out to be like this: I h guard d psi dt equal to minus h guard square by 2m d2 psi dx2 plus v psi. This is time dependent Schrondinger'S equation, one dimension equation. As you can see, here is the only function is x, means it's along the x axis. If you watch the video and if you got help from it and like the video, to please hit the like button, and if you like even more, then subscribe it, and you can even share it with your friends. So that's I have to say.